Present you one of the most actually powerful techniques to train neural network with actually limit number of parameters, but to achieve better results than the neural network actually can achieve. Okay, so the technique is actually distilling the knowledge, or distilling it, like enrich your knowledge, your power of your of the neural network by using ensemble of more powerful neural networks. Okay, so we will use more powerful neural networks for enriching enriching some low computational neural network. Yeah, actually our benefit will be its low power and complexity neural networks that achieve state-of-the-art result for this neural network. Okay, so it's actually the idea. So actually, we will talk about ensembles. We will talk about distilling, results and conclusions, and the actually existing research topics. So training ensemble. Okay, so actually, let's start from overfitting. So as you know, ANN or DNN is easily overfitted to train data. Yeah, it actually happens because we have more parameters than our trainable samples. Yeah, so it's actually a known phenomena, and we have a lot of techniques how we can to deny it. Yeah, so it's actually all regularization techniques. Most of them we presented before, like Bayesian normalization, weight decay, and other techniques. Okay, so to improve our generalization performance, we could ensemble few neural networks. What actually we can take a few neural networks. Okay, they will actually be solved the same problem. Okay, they need to train to the same problem, and actually we have here our input. Yes, that he will actually spread for all of them, and we have our output. So we can actually take our results of each one of the network and make some ensemble on the last stage. Okay, we actually will take we will take the best result. We will take the best of each of them and we'll combine them for one. So because of our ensemble is composed of many models, ensemble is computationally expensive. Yeah. So actually test sets are large, like Google, and storage spaces are actually very premium, like mobile phone. Yeah. So we have limited resources, but we want to achieve great results. So how we will do it? Yeah, we can train on our mobile, or we can inference on our phone all these networks. Do you agree with me? So it will actually, it's not feasibility. You have no batteries that can no batteries that can support this kind of okay. So VGG networks require an amount of 500 megabytes of storage. Yes, number very big. ResNet takes around 25 megabytes, but it's still a lot of, because it's actually storage that need to be fast storage. It's cache. Okay, it's not it's actually your parameters that you need for in your execution of algorithm. So you need very fast storage, and you can afford yourself to use this amount of storage, because storage take a lot of money. Okay. So it's not suitable for mobile device or drones, automotive, etc. So what we are going to do, we are going to use actually single model, distilling ensemble. So we want to get a single and shallow model that will achieve good performance, but give us low computation. Okay. So actually we have here input output. This is the if you will use all ensembles, yes, but instead we will do this. We will train only and inference only. Actually, we will train not, but we will inference only one model. Okay. So if we will use many observations, our generalization property will be good, because as I said before, we will take the best from each of network, and we will actually merge it in one. How we will do the properties we will see in a few minutes. So if we use many observations, our actual generalization property will be good. Okay? So it's actually our ensemble. Yes, and we have here a few examples, and this is our single model. Okay? So in this single model, actually we can see our classes. Yeah? So if we have more samples, we actually, of course, our network work better. Okay? But it's problem to we don't have many observations. Okay? So we need good algorithms that will work on a restrict number of observations. Okay? So how to do it? Great. So we don't have many observations. We actually have here. This is some observations. We have. It's actually our. It's a cat and giraffe. And dog, okay. So it's actually these parameters. Okay. It's weight, color, length. Okay. So if we will do it on actually this shallow number of samples, we will get a perfect oversample. Yeah. So here we will do it again. Yeah. It's actually so. What will be the results of here? So we can actually we don't have a class label for them. Okay, for other investigations because they actually didn't we didn't have them. Okay. So to solve this problem, we will build an ensemble model that will use original data. So this is our sample model. He will use original data, and this way we will add class using prediction of the ensemble model. So take a look. We will take our classes that we actually predicted, and we will add them is like synthetic to our model. Okay. So here we will add the cats, and here we will add the cats, and this way we will actually have more sample training. Okay? Only by using ensembles. Okay? And each of them is actually trained on the same number of samples, but we actually each of them have his point of view on the classification. Okay? Great. So finally we will train a single model using this increased data. So we increase data, use ensembles, enrich our sampling, and now we will actually we will train this one. This one is more examples. We will have here more examples, and we will train only one neural networks. But we take from the others their point of view and their actually classes, in this, their class predictions, and we predicted other methods. Okay. Great. So now we have actually 3 classes. They actually have a lot of samples of each of them, and we will have here was our input. Okay. Take a look. This was actually restricted input. Yes. And we take our ensembles. We took the predictions, actually the softmax predictions of each of them. Yes. Used for predict more samples from our classes, and get actually rich data. This data is actually easy to learn because you have more samples. And the overfitting here is less. Do you agree with me? Anyone agree with me? Anyone who not agree with me? Questions? You can ask. It's okay. Okay. Yeah.
How do you generate the samples?
How do you use the samples? Yeah. Right. How do you use samples? I actually take you will see more mathematically later, but let's look intuitive how to do. We actually take our input, okay? We give the input, and we take the softmax of each of them. We take a sample. We take actually some number, we take his representation, the softmax, and then you generate new data using actually auto decoder. Okay, I didn't mention it yet. You're using decoder for sample from each distribution. Okay, I need to read. Okay, 1 minute about the way how you generate your samples. Actually, it's like encoder-decoder model. Okay, encoder model. We actually take our sample. Yes, we give some low representation, feature representation. Yes, and then we actually reconstruct our. We take ensembles because we have a lot of actually point of view on each sample, and you reconstruct from these ensembles. Generate your data. Okay, but you actually use it works because you actually use. More detail. You have actually merged the details. Your data is actually your data is not similar to your original data. Okay, it's ensemble data. Yeah, please.
It might be not a good idea when you have overlapping two distributions of two classes that you're trying to classify.
Can you please speak louder?
Imagine if you have two classes you want to classify. Okay?
Yeah.
And the distribution that you're trying to learn with again, for example.
Yeah.
Like both of the domains are like have some overlapping.
Yeah.
So it might not be a good idea in this case.
In this case, no. But look. First, I remind you that this is not a generator. Yes, it's not a coder model. It's a coder model. So you're not. Actually, you can. Okay, it's more details, but you can use KL algorithm for take examples that are not that have not that are diverge. Okay, you have that they're not overlapping. Okay, you can do it. It's details. How you actually you can do some you can use some you can use some yes, you can do notations. You can use you can take some vision style looking only on choose only the samples that have actually low overlap. Yeah. Okay. Yeah.
So what you're suggesting here is basically to use an ensemble to prevent overfitting because we have a small data set.
Yes.
So, like, how is that better than just regular regularization to prevent overfitting? Like, how do they compare? If I train a single model with regularization versus this.
I got your question. It's a very good question. Look, if we will take if we will take some assumption that our results depend on the number of your samples that actually are different samples. Yes, so you have some local minimums that you can get from one data set and other data set. From the other, actually, the number of parameters are the number of samples are have some have actually it's influence on the number of on your final accuracy.
Mhm.
So what I want actually what I want to tell you that using overfitting is one problem. Using actually using shallow sample datasets is the other problem. So you prefer to defeat overfitting than defeat small dataset problem. Okay. Yeah.
What is different between the models, the initial?
Yeah, you asked what the difference of these models?
Yeah,
It's
aside
actually,
from the
look,
initial guess.
Okay. It actually can be ResNet 18, ResNet 34, ResNet 15, ResNet 101, ResNet I can continue. Okay. Actually, you take okay. So we'll talk about it later. But you actually take more powerful neural network because you want better ensemble than the original one. Okay, you actually you want this neural network that can achieve better results because he will give you more his probability on softmax as more accurate. Yes, this idea. Are you figure out this idea? Very good. So let's take a look on this graph. So it's actually our RMSC loss. Okay. So if actually we can see here so that more training data, less error. Okay. It's for you. More training data give less error. Okay. It's one of the investigations of this point. So when you took an ensemble, when you took more actually data, ensemble data, you minimize your errors. Okay. So it was actually one of the investigations of using ensembles for generating new samples. Okay. Okay, so we can use predict class of ensemble. Okay, we can use our predict class of ensemble for actually for enriching our training set. So, but we can select another approach. Yes, I actually gave you one approach, generating the data from ensembles, enrich your data. Your training data, and then achieve better results. But actually, this approach is computationally a little bit heavy. So let's do something else. Okay. So Hinton et al. Proposed in their work distillation technology in your network some ways. To enrich your actually not generate your input data and then enriching your data, but using your investigation from ensembles to actually force your softmax of your shallow model to be better. You're forced. How is it? So if we use the probability of the class in the lesson property, it will be good or better. So we can use logic instead of our class. So what is logic, guys? The logic is actually your score for each sample. Okay? It's a number that actually give you probability. It's not probability. It's actually what. It's not logic. It's actually the number that he actually from minus infinity to infinity. Yes, it's not restricted. It's not restricted, and it's actually actually the better logic score is actually the neural network is sure that it is the class. Okay. So, for example, I give an example. I give our sample cat. Okay, and my score is 2. That it is a cat. Okay. So actually, and here I gave a dog, and my score is -2. That the neural network is not sure that it's a dog. Okay. So the more positive number is says that you actually more your neural network is sure that more sure that it is the class. Okay. Okay. So logit is actually from logit we actually build our softmax because using the logit we are taking we will see in a minute. We actually building our probability. Yeah, because softmax is actually probabilities. The best probability, argmax of its probability, it's our one hot vector of the class. Yes? Is you find? Yeah.
But how is it for ensemble?
Yeah.
You mean you count?
Yeah. I didn't.
Yeah.
The explanation will be in the future.
Yeah.
You don't know how now the
Because otherwise I will just use it.
Yeah. No. Now you don't know. You don't know how. You will know in a few minutes. Okay.
Okay.
So logit would be the same as score of class we are talking about before. So now we actually then we have our score. We use it. Great. So we have our input. Yes. Actually, it's some you can think it's actually some output of CNN, okay, of convolutional neural networks. It's just numbers, yeah. Now you have it's actually the final fully connected before softmax, yes. So we have some some weights that you distributed. Gaussian distribution, yeah. So then we have some actually numbers, yeah. So we have the multiplication results, okay. And then we actually applied some nonlinearity here. We applied some nonlinearity that actually have some fixed from 1 to 0, and get some numbers, okay. And after then. Okay, it's actually the results, but not afraid of results. Multiplications of it's actually it's a multiplication of each weights on the neurons. It's fully connected there multiplication. Okay, and then we have other weights on H. Okay, one before, and here we actually see some scores. Okay, and we have the final one. It's actually, this is the numbers. So okay, great. So we have here our numbers. And then, here we actually have our probability. Okay? So the probability that it is the cat. It's actually the probability. So I will choose that it is the cat. Yeah? Because it's scored.
What is the scale 0 to 1?
Here, it's a tangent function. Okay. So great. So again, we have here our actually our sample. So now we actually see that we will take all our neural networks, all our actually ensemble, and we'll have actually two. Yeah, and we will replace it for our score 2. Great. We can use logit instead of class. As we said before, it's actually an investigation that published by Ba et al. Okay, it's actually the papers. If you want to read it after that, it's published in NIPS, our senior conference. So it's a good work, yeah. So it's actually give you option not to do a lot of computation of softmax. You can actually only work on this course. Great. Now pay attention to this. We can use single model, actually, second modification. Here we can add noise to logic, which acts as regularization. Okay? So another work investigated. One interesting part that if you will take your score, before score is actually what the neural network thinks that will be the actually how it should the record should it is the class, yeah. And we will add some epsilon, actually some noise. It will be some Gaussian, okay? Yeah.
אני מצטערת, לא הבנתי איך הרמת ביטחון הזאת, ציונים שהרשת הראשונה נותנת לעצמה, הם מוסרים לרשת.
לסופטמקס? יש לך נוסחה של סופטמקס, ושם אנחנו נסתכל, יש נוסחה, אני יכול, כאילו, אז יהיה לוק, אבל תזכרי את זה, אני תכף אגיד. טוב. Okay, so let's move. So here we actually have our epsilon, yeah, and we actually adding the noise actually improve our results. Okay, so it's other work that we take into investigation of it, and it's great because we know that noise is actually adding noise actually on every stage of the neural network is very it's help regularization. So it's a very interesting investigation, but predictable. Okay, so it's actually you can see it here. So noisy data is training help to regularize a model. Here actually the Z it's our logic. Z hat actually our predictor, and they actually take a noise from a Gaussian distribution. It's actually the most useful and most important noise in neural networks. Okay. Actually, it's if you will ask me why Gaussian, one of the answers is actually most of the assurance of how HGD work is stochastic gradient descent. So it's actually minimize your error by giving distribution of weights to be normal. Okay, it's one of the investigation of it's one of the actual investigation of how a neural network is training. So it's, actually the data are the weights and activation are used to be distributed normally. So using normal using normal Gauss, editing in normal Gauss is always work pretty good. So now we want to minimize this one, but we actually taken some MSC. Yeah. So we want to minimize it without restriction on noise, and we have actually our error have our Z logic and our noisy part. So we want to minimize it. Okay, so Hinton used softmax function to get probability distribution. I will give you 5 minutes. You want? Yeah. Anyone need five minutes break, or we will continue? Okay. So Hinton used softmax function to get probability distribution. It's actually our model 3. Okay. So again, we have our part. So we have our data. We are not enrich our data by sampling. We will use some more sophisticated distillation. So it's our Technion ensemble model. Okay, and we have actually this is our data, and we know that we have more powerful neural networks samples. We are calculating probability with softmax function. Okay. Okay, so actually we have our probabilities. Okay, now we will do the prediction, and it's our probabilities. Okay, it's our calculated probabilities for each one. Okay.
Do you mean we're using an ensemble now and calculating a softmax on the output of each model in the ensemble, as opposed to before where we had a single model and used the logits from the single model?
Yes.
Okay.
Yes. You're right. So we'll obtain our probability and use probability as our actually as our we will take probabilities of ensembles of each neural network. Yes, and now actually we will use it instead of our shallow model probability. Okay. So actually, how it works? Let's do it. Let's show the algorithm. We are training a lot of neural networks, taking the probabilities, enrich in one more shallow neural network, and then we are learned. We actually our backpropagation we're doing on this shallow neural network. So you're forcing your softmax by powerful neural networks, but making your backward on a shallow neural networks. So in this way, you actually can enrich better results than your neural network can achieve, because you're actually like forcing, you're pushing your neural network, yeah, because you are making it actually you will take your car that have speed limit once, and you will actually enhance your you will actually drive faster than your limit. How? Because you will take more faster car, and the more faster car will actually help you from the back, will push you a little bit. It's actually what happened here. You are pushing your model by using more powerful models. Is it understandable? Are it? Do you have any questions about it? Still? No. Okay, great. So, you have our probabilities, and now, so it's our trained single model, okay? And probability acts like, yes, probability likes our regularization. And here, okay, you ask, now we are talking. So, when you actually, let's talk before t is actually some parameters that we talk about him now, but before t is actually our softmax, yes. So actually, when you're taking your score is here. So your score is actually help you to, it's not help you, it's actually the bigger, if you have your big score for I class, okay, so you have here normalized more the bigger number, okay? So it's actually your bigger probability, okay? Because it's actually here, במונה, okay? המספר יותר גדול במונה ולבאז מנורמל, okay? It was an English. Great. Now, so here we actually have our probabilities, yes, because now it is one, yeah. Okay, so we will take our activations, and we will have we will do the same trick. So another activation function is sigmoid function. Yeah, sigmoid function is actually from 0 to 1. So it's very good. So the sum of the sigmoid value is not 1, but the sum probability distribution have to be 1. Okay, so we understand because we are normalized the sum. So it can be more than 1. So to make some one, we use softmax function. So it's actually our softmax function, and we actually now we have explanation from score, and now we have our probabilities. Yeah? Okay. So now I will add one parameter to my softmax. This parameter is temperature. Okay? I will not explain you the all assumptions that Hinton give on this temperature, because he actually have some theory on why it's actual temperature, and why it's why he choose to use term of temperature. Okay, but it's actually parameter that if I actually give him more than one, or when I actually give him more than some threshold, I will actually I can more influence on my activation function, on my softness. So if I actually take an example and I give more temperature for, if actually I want to enrich some my shallow neural network by softness from other neural networks, when my temperature is bigger, I actually force my softmax of the shallow neural network be more powerful by actually ensemble. Okay, and if I take my t smaller, actually my the power of the ensemble neural networks is less. Okay.
Which
Yeah.
of the numbers here come from the shadow network, which belongs to the
Okay.
example?
Okay, great. So this is okay. So this is the numbers of my shallow neural networks, and this is the numbers of my ensemble networks. Okay. So this is my neural networks that actually I take from. Okay. So if we can see here, where we actually from some of the temperature, yes, we can look at here from this temperature and actually and bigger temperature, we have okay, so it's not it doesn't matter. Okay, so till some number we actually can change the proportion of each and of your teacher on your student, and from some number, it actually you have no this number that will give you for the all temperature numbers, it gives you the same value. So you actually need to choose if you want to actually check how our teacher is actually can improve our student. We need to take the value that actually someone here. Okay, something here. Yeah, because here it doesn't matter. You can see it's actually this number will not give you improvement. Okay. This is actually, again, this is class probabilities. This is 3 class probabilities. Okay? 3 class probabilities, it's probabilities of some sample. Yeah.
What does the colors represent?
Color represent your probabilities of the different neural networks.
The different approaches?
Yeah, no, not approaches. The different. You train with different neural networks. So each neural network have some probability of each class. Yeah. Different approaches. Yes, you can say different approaches. Different neural networks that solve the same task. No.
So it's assembly of size 3, and each of the colors is a member of the assembly?
Yes. Okay. Now we can see here. We can see that in this actually in this version, we can our T can give us actually we can mix between our probabilities, because this neural network seems that the probability of this class is very high. This probability of the class is very low. So if you want to distilling keys, you will need to find some. You will need to use T where somewhere here. Okay.
So is it like a way to enforce consensus or something? To like have a consensus?
Yes.
Window?
Consensus? No, only empirical results. There's no consensus. Only empirical results. Hinton have no explanation about the optimal T. He have only explanation of what is happen if you take a bigger T. Bigger T give you actually no benefit. Okay? But actually, what they did, they actually make consolidation of the T, varying the T from 0 to then from each neural network, they find the optimal T. Okay, that achieve better result. Do you understand what is ensembling and what is T and why we need to use it? How it works?
I still don't understand how the shadow network uses the information from the sample.
Very simple. I give you a picture for cat. My shallow neural network gives probability of 0.4 that it is the cat. I will take, but I'm not convinced. Okay? I will take some powerful neural network, will train it, okay, and then the result of can be its bigger probability or smaller probability. So when I will distill it, I will have more. I will my result. Look, I will soften, yeah, because I will actually, if it's cat, so I will give him priority. It's actually I will give him, it's a cat. If it's not cat, it's my powerful neural network will actually observe that it's a dog. Okay, so it will give him less probability.
Can you do it only when you're not sure?
No, what do you mean by that? No, you're doing it in all training process. But if you're shallow neural network and you're powerful neural network, you achieve the same result. It's okay. So merging will be the same result. Yeah, it's like soften. It's like you take function and you make it more soften. You're cutting the peaks, cutting the peaks. Yeah.
Wait, so what I'm missing here is that it seems to be that the loss function, when you train the shallow network, the loss function should somehow incorporate the data from the ensemble. So we don't see that here. When you train the shallow network.
Yes, you're right, because I didn't show you the loss function.
Okay.
But
so
yes, your loss function.
So this is like the step before. So the softmax layer in the shallow network.
Yeah.
Computes the probability that the shallow network thinks, for example, of a cat.
Yeah.
And the incorporation of the probability from the ensemble should happen in the loss function after that.
Yes, you're right. You have a lot of methods how to do.
So how does the temperature help us incorporate the data from the ensemble? Because this happens before the loss function. This is like the input to the loss function.
Yes, but you. I understand your questions. I will proceed.
Mm-hmm.
If you will not, if I will not answer your question, let's talk about it later. Okay. But there are a lot of. I will give a few words. There are a lot of ways how actually to take how to apply your distillation. Because you have actually one of the methods is taking every time. So no asking. When I am assembling, when I'm taking the knowledge, I can do it every time. I can do it only for the true from the true labels. It's actually if both of my networks are think that it's the true label, yeah. And if it's not true label, so one of them is actually lying, so I will not take it, yeah. Because if I lie, so why do we need to take wrong information? Okay, and I can do random. I can actually do some random initialization. Okay, so I have a lot of ways how to add your impact of the neuron. Okay, so here is actually what you see here. The temperature T is actually it's when I think I have there another explanation, but it's actually after I choose my once, in seconds, and I will combine them, okay? I will take few softmax, yeah, and then I combine it from one. The way of combining, there are a lot of ways, a lot of strategies. But most of them, I think that random, if you're asking me, I think that the better results achieve the random visualization. Actually, it's the better. Okay. So, but let's continue. I think that I will give you that version later on. I have here this version. So there is no difference between samples. Okay. So according to Hinton, original softmax function T is actually 1, gives a higher probability. Is actually probability is valid to correct classes. Okay. So therefore we need to set temperature more higher than 1, i.e. from 2 to 5. Okay. Again, it is observation from given data set. It's not observation for it's observation. He did not test it originally on ImageNet. Okay. He did a mistake because on ImageNet it doesn't work. So those of you who will choose this actually very fascinating project will work on how distilling the neural network on ImageNet. Great. So we need to set the temperature. Okay, so it was his investigation from some given data set, and we can take it like assumption. Yes. So all observations have same probability. Okay. Appropriate our temperature, we have different probability. Okay, and actually for this one we have bigger probability, and from this one we have small probability. So this is our probabilities. Okay, so we have here 1, 0, 0.8, and 9, etc. And here is actually our region that we are working. But here we are making here we actually can have advantage of using our distribution. So training single model. We are training single model by using other methods. So our cost function. So our cost function is variant of cross entropy. Okay, it is our cost function. So it's y. You are actually summing our probability. Our y actually our labels multiplied by log of each probability. Yeah, it's actually only in the place actually. Y is our original y, so only in the place when our hot factor is 1, yes, we actually have some loss, we have some value that we need to minimize. Do you understand why? Because y is actually, y is actually our hot vector, because we have for actually our label is hot vector, because cat can be cat, so it's only one class. And then you are actually multiplying by log probability, and actually if your probability, let's take a little bit, let's talk about math. If you're actually in the place when you have your 1, yeah, you have big, you have higher probability. So what happens? It's the loss is lower, yeah? Again, you multiply 1 by probability in the same place. If your value is small, what it means? I have cost function. My cost function is what I want to minimize my loss. If I train more, okay, and for the sample cat, it will be the first hot vector that it's the first class, okay? So it's 1 and zeros, okay? Depends on the number of classes. If your probability that it is cat is higher, it's high probability. So around 1. So your number is small, yeah? And if the probability is around 0, so you have actually your probability is your loss function is high. So and then you actually we will back propagate. We will do back propagation on it.
What
Yeah.
is the theta T in the Q? Is that the temperatures for each
Yeah, it's temperature
for each of the ensemble results? Ensemble.
yeah, it's a temperature for each of them.
Okay. So each ensemble result has a different temperature that controls how we mix them.
Yes.
The
it's-
mixture creates the Q probability that we think it's the real cat is actually a
It's-
cat.
it's a-
How
it's a
much of a
cat.
cat is the real cat?
And then we actually backdrop on this
Yeah.
on the original on the shallow model.
Yeah. So
We are taking our ensemble, give some calculate our probability. Yes, actually depends on the powerful neural networks, some examples from them, and then we want to actually to learn to model that it will be to recognize that it's the cat.
Mhm.
Okay, it's very fascinating and interesting. So Q is probability of softmax ensemble. P probability from Y to be K actually depends on Q x and then probability of single model. K is actually our class index. Yes, it's actually which class we're talking about, and V is total number of our classes. Very good. So we want to maximize objection of this function. It's actually our indicator guys of true class. It's a predicted probability of true class, our model. Okay? It's very simple. It's actually it's our objection that we want to maximize. Okay? Maximize objection is minimize true. Okay? Very good. So from objection function, we actually get the cost function, you know, cost entropy, everybody knows. And now we have actually our cost of t, and now the cost function is variant of cross entropy, yeah? It's actually our outcome. Then Q is probability of softmax with ensemble model, actually what we talked before. So Pyx is probability of single model, K is class index, it's total numbers, and we use probability of ensemble here rather than indicator function, okay? So we force the model to achieve better results. Hinton et al. Found that using original set together works well, maybe due to original target information. Yeah, because it makes sense, because you want your information is actually dictated by your original. So it's our target, it's class probability of ensemble, okay? Target is a class of original data, okay? And now we will train this model. So let's again take a look, guys. It was 3 years ago, and he talked to here about MNIST. You know, now MNIST is like it's less than toy example. Okay, today toy example it's CIFA. These days toy example was MNIST and CIFA was actually the huge data set. Okay, so now MNIST is actually I'm review on also papers who present the data on MNIST, result on MNIST. It's like he need to actually cover to not to present it on some more realistic. Okay, great. So 2 hidden layers, 1 relo, 2 hidden layers, relo dropout, and 2 hidden layers, relo softmax target. It's actually the number of tests that they done, and the results 2 was on speech recognition. So the system was baseline, 10 ensemble give better results, and distilled single model gave almost actually the result of the 10 ensembles. So using distillation model is actually as good as using 10 networks. And we are not training here 10 networks. Okay? We are only using the entire ensemble. Great. So single model can be built using artificial data or soft target. and it's actually give us very good performance and low computation, and it's actually connected about we talked before on a computation on the hardware to for hardware for deep learning algorithms. So we prefer that algorithm to achieve better result, actually less power than using more powerful hardware. Okay, because we have a limitation that we talked before when we use on embedded devices. No, mobile drones. Okay, so now we're done. Thank you.